Good morning, student.
Good morning, sir.
How are you?
Good morning, sir.
How are you?
Yes, sir. Well, fine.
Morning, sir.
How has been your lecture so far?
Fine, sir. Yes, sir.
Yeah.
Fine,
So,
sir.
this week is the last week of virtual lecture, right? Are you aware of that?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
So you now come physically to UI to be receiving your lectures.
Yes, sir.
Hope you guys are ready.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
I wish you all the best.
Yes, sir.
Yes.
Thank you, sir.
And when you enter, please do any regulation you are supposed to do, so that we don't create a problem for yourself during your assessment. So today's class is just it's going to be just a summary of what we have been doing. So within a short time we finish, so that I can take questions as many as possible. So, but you need to reserve your question to the end. I will not take much of our time. Maybe within 15 to 10 minutes, I'll be done with the summary, and we interact. We interact very well today. So probably you have something that is on your mind, to either concern the course or concern UI generally, or concern your department. So you can ask me. If I have an answer to it, I will gladly attend to it.
Oh my God, you do this one.
Who's your God? So let me make somebody a co-host, so that anyone disturbing the class, we can mute the person. Okay, somebody is raising. Why are you raising your hand? Anything? So, okay, Olasunkami. I think I've seen Olasunkami again, but I've not seen that. I saw his face here, but I cannot see on the list here. Olasunkami. Okay, let me search. Olasun. Oh, it's not for Olasun. I did this survey. Okay. Let me make him a co-host. Make Olasunkami a co-host. Olasunkami, you have been made a co-host. So you have power to meet or omit people. Let me look for another person, one more person. All right, let me make Ayeni Josiah a co-host. Ayeni Josiah, you are a co-host. So you have the power to mute people or to do some necessary settings that will be favorable to us. I've not seen it again. Okay, Ayeni. Okay, yes, Ayeni is now a co-host. Yes, your last is coming up. I think I've made the last time a co-host before.
Yes, sir.
Okay. Okay. Yeah. I did. Yeah. So let's start the summary. Within a very short time, we'll be done, and I will listen to different comments from you guys and questions. Let me make all so that the class can go smoothly. Share my screen. Good morning once again, students. So you're welcome to Physics 103 class. Today's the 6th week of virtual interaction. And today will be a summary of what we have been doing the past 5 weeks. So we started from heat, temperature and heat. So, and I told us that it is just the transfer of energy from one object to another as a result of difference in their temperature. That is to say, before energy can be transferred from one body to another, there must be a temperature difference between the two objects or bodies. So condition necessary for energy to flow between bodies, as I said, the first condition is that the two bodies must be in thermal contact. That is, thermal contact must be established between the two bodies. Another condition is that there must be difference in their temperature. That is, they must not be in thermal equilibrium. If the two objects in thermal equilibrium, no matter how the thermal contact you establish with them, it will not flow if they are in thermal equilibrium. That is, if they have the same temperature, energy will not flow. Take note of that. Then another thing which we know right from our second is that it always flow from a body at higher temperature to the one at lower temperature. So what's the meaning of thermal contact? Two objects are said to be in thermal contact with each other if they can exchange energy between each other. So if two objects can exchange energy between each other, we said they are in thermal contact. They are in thermal contact. They may be in thermal contact and not exchange energy. I believe you understand that now because I've explained before that even though they are in thermal contact, they may not exchange each between each other. It means the two objects are in thermal equilibrium. And another thing we look into is zeroth law of thermodynamics. Zeroth law of thermodynamics, and the law states that if two objects A and B, which are not in thermal contact, so objects A, they are not in thermal contact, they are separated. They are not in thermal contact. If the two objects are separately in thermal equilibrium with third object C, then objects A and B are in thermal equilibrium with each other. So I said if you have two objects A and B, and they are not in thermal contact, thermally we have separated them, but we pick the first one and compare with the third object C, and we say, let's say we pick A first, the test is object C, and we say that A and C are in thermal equilibrium. Then I pick the second object B to test that object C again, and I see that B and C are also in thermal equilibrium. Then I can conclude that A and B are in thermal equilibrium and thermal equilibrium. So what's the meaning of thermal equilibrium that you are seeing? So the layman language of thermal equilibrium is that equal temperature. That's the layman language. So if they say two objects are in thermal equilibrium, it means two of them they have the same temperature. And if they have the same temperature, they cannot each cannot flow from one to another. That is, they cannot exchange each energy by each. Then thermal equilibrium is a situation in which two objects would not exchange energy by heat or by electromagnetic radiation if they were in thermal contact. They were in thermal contact and did not exchange energy by heat or by electromagnetic radiation. We say they are in thermal equilibrium. So let me record. Okay. Okay, let me allow you to record. Oh, sorry. Let me run over it again so that it's smooth. I said it is a transfer of energy from one object to another as a result of difference in their temperature. So, and I give us conditions that will make please don't disturb me with this request. Apply this function to. Okay, let me give you the profile. The two bodies must be in thermal contact. That is, thermal contact must be established between the two bodies before they can exchange energy. Then another thing is that despite the fact that there's thermal contact between the two bodies, before each can be exchanged, the two bodies must not be in thermal equilibrium. The two bodies must not be in thermal equilibrium. So we know each always flow from a body of higher temperature to a body of lower temperature. So, and I give us the meaning of thermal contact. Two objects are said to be in thermal contact with each other if energy can be exchanged between them. If energy can be exchanged between two bodies, it means they are in thermal contact. If they are not in thermal contact, it cannot be exchanged. So let me explain the meaning of this thermal contact that I'm saying. This is not a physical contact between two bodies. It is very possible you put two bodies beside each other and they are touching, and they are not in thermal contact. It's very, very possible. If one is insulated, so let's say I put this bottle against this bottle, and I put an insulator between them, so they are not in thermal contact because it will not flow between two of them. It is when it can flow between two of them that we say they are in thermal contact. Physical contact does not always mean a thermal contact. You have to take note of that. Okay, I said zeroth law of thermodynamics. So I said this law says that if two objects A and B, which are not in thermal contact, are separately in thermal equilibrium with a third object C, then object A and B are in thermal equilibrium with each other. So we take two objects, which we call one A, we call the other one B, and the two objects are not in thermal contact. That is, they have been separated. Thermally. So we now pick the first object. I test this third object C. I see that the two of them are in thermal equilibrium. I pick the second object B. I test with that object C, and I see that B and C also are in thermal equilibrium. Then I can conclude that A and B are also in thermal equilibrium. So that's what I said. Then I explained the meaning of thermal equilibrium, and I told us that the layman language of thermal equilibrium is just equal temperature. So two objects are in thermal equilibrium means two objects are that they have the same temperature. So this is the definition of a situation in which two objects will not exchange energy by heat or electromagnetic radiation if they were in thermal contact. If they are in thermal contact, if two objects have the same temperature, it will not flow from one to the other. So take note of that. So that's where we were before the interruption. Then temperature scales and fixed points. So the most common temperature scales, as we know before, we have a thermodynamic scale, we have Celsius scale, we have Fahrenheit scale. Thermodynamic scale is also known as a Kelvin scale, and the highest point of this scale is 273.15 Kelvin, while the steam point is 373.15 Kelvin. The fundamental interval, that is the interval between the upper and the lower points, is what is called fundamental, and it's 100. It's 100, the 100, yeah. Then triple point of water. Another fixed one that we have is triple point of water, which is at 273.16 Kelvin. 73.1. We have said this in class before. So the second scale that we want to quickly look into is Celsius scale. The highest point is at 0 degrees Celsius, while the same point is at 100 degrees Celsius. The fundamental interval is also 100 degrees. Then triple point of water, in this case, will be 0.01 degrees Celsius. Take note of that. That's triple point of water. So the third one is Fahrenheit scale. Fahrenheit scale. The highest point is 32, and the same point is 212 degrees Fahrenheit. The fundamental interval between the 2 points is 180. Then, what will be the triple point? I leave this for you guys to do. So, since we have done a conversion formula, how to convert Kelvin to Celsius, how to convert Celsius to Kelvin, how to convert Fahrenheit to Celsius, or Celsius to Fahrenheit. So, I said the triple point of water on Fahrenheit scale will be what? So, you guys should try and do this. Lay your hand on it. Then all these are at the atmospheric pressure of 760 millimeter mercury, except the triple point of water. I remember the triple point of water is at pressure of 4.60 millimeter mercury, and that's one of the reasons why there's a difference between the triple point of water and the ice sponge, because they are not at the same pressure. And the water used for triple point of water, this water used, the dissolved air has been evacuated from the water. So I gave you the two reasons why triple point of water is different from ice sponge. You will see that they are very, very close. So those are the two reasons. The dissolved air has been removed from this water used for triple points, and again, the two of them are not at the same pressure. So relationship between the temperature, the Kelvin, and the thermodynamic scale. So I gave you this, that if you are given temperature in Celsius, which is called TC here, if I want to convert to Kelvin, I'll just add 273.15 to it. Or if I'm given temperature in Kelvin and I want to convert it to Celsius, I'll just remove 273.15 from it. So these are the formula to convert temperature in Kelvin to Celsius, or temperature in Celsius to Kelvin. Then I said note, the difference of two temperatures on Celsius scale is the same as the difference of their corresponding temperature on Kelvin scale. So this thing we did in class, and I used two equations, and we see that we have the difference in Kelvin is the same as difference in Celsius with the two temperatures. So take note of the statement is very important, because many times they might not give you the two temperatures. They just give the difference, and they say we'll find the difference in the other scale. It's very important. The relationship between Fahrenheit scale and Celsius scale. So I gave us this formula. The formula to convert Celsius temperature to Fahrenheit temperature. So you can do otherwise. You can make a TC, the Celsius formula, so that when the temperature is given in Fahrenheit, you can convert it to what's it called? To Celsius. So, and that one will be what? That one will be what? Okay. Oh, sorry, I've muted you guys. So that one will be TF minus 32 multiplied by 5/9. If you do your mathematical manipulation very well, that's what you get. Then I said note again, the difference of two temperatures on Fahrenheit scale is 9/5 times the difference of their corresponding temperatures on Celsius scale. That is, when you take two temperatures, when they give you two temperatures in Celsius scale, and if you find their difference to Fahrenheit, and you check their difference, see that the difference you get in Fahrenheit will be 9/5 times their difference in Celsius scale, or that of Celsius scale is 5/9 times the difference in Fahrenheit scale. It's very important to note that. Then we talk about thermometer calibration. Thermometer calibration, and I told us calibration is the process of standardizing a measuring device to ensure that it measures within a specific range in which it is designed to operate. That's just calibration. But now, specifically, we say thermometer calibration. So that will be the process of standardizing a temperature monitoring device or instrument to ensure that it will measure within a specific temperature range in which it is designed to operate. And instead, how we can calibrate thermometer by placing it in thermal contact with any of the natural systems. So that's how to and I told us this natural system does not mean that something that God created. You know, if you say natural system in biology, you say, oh, it's something that can breathe. You know, here in this sense, the natural system can be any of the defined fixed point we talk about, maybe the steam point or the ice point, as the case may be. So take note of that. Then there are problems with thermometer calibration. There are two major problems. The first one, that extreme accuracy is not achievable. Extreme accurate data. You want to calibrate this thermometer that will measure exactly the temperature of the body. So that's no. The extreme accuracy is not achievable. Then the second problem with the thermometer calibration is that they have limited range of temperatures over which they can be used. Like some can measure very low temperature, some can measure very high temperature, and so on. Like mercury thermometer now can measure a high temperature, while alcohol thermometer can measure a low temperature, and so on and so forth. Then types of thermometer. We talk about type of thermometer. Different type of thermometer. We have liquid in glass thermometer, which I give us one example now, like mercury in glass thermometer or alcohol in glass thermometer. So we have constant volume gas thermometer, we have electrical thermometer. Another electrical thermometer, we have like 3 of them. So you have said it in the lecture. Then another thing we did was thermal expansion of solid and liquid. I told us that if the temperature of a liquid decreases, when it decreases the temperature of a liquid, or increases rather, its volume also will increase. Its volume also will increase. But there's an exception to this, which is water. You know, when I increase the temperature of water, let's say the water is around the -4 degrees Celsius. -4 degrees Celsius. When I increase the temperature, water will expand until the temperature gets to 0. When temperature gets to 0 and you're still increasing temperature, water will contract. Instead of expanding, it will begin to contract. You know, this is an unusual behavior. So water will contract. Then once you get to 4 degrees Celsius and you are still increasing temperature, water begin to expand normally the way other liquids do. So, and this is what is called anomalous expansion of water that we did in SS1. So then, okay, I've said it. For solid, as temperature increases, its dimensions also increase. That is, when you have a solid, when I increase the temperature, the length will increase, the breadth also will increase, the the height also will increase. And this phenomenon is called expansion, thermal expansion. Thermal because the expansion is brought about by heating, that we call it thermal. Thermal expansion. So I said if the thermal expansion is sufficiently small, that is, if the expansion is not too great, that will break the bond in the bond between the atoms of the object, then this relation hold. That is, change in length over original length is equal to coefficient of linear expansion times the temperature change. But mind you, the expansion should be sufficiently small before we say this relationship holds. So that if I cross multiply, I can have my change in length. Maybe they ask me to calculate the increase in the length. If I increase the temperature of a particular object by particular amount, then they give me the linear expansion of that materials, and they give me the original length. What's the original length of that material before I start increasing or decreasing the temperature? So to get that little increase in the length that the increased temperature or decreased temperature will cause, so I just use this formula, the linear expansion, the coefficient of linear expansion multiplied by the original length multiplied by the change in temperature, where delta L, delta T, and delta L are defined here. Delta T is the temperature change. Delta L is the change in the length, while Li is the original length. Li is the original length. Okay. And alpha, as I said before, is the coefficient of linear expansion. Coefficient of linear expansion. So that's for length. But if it's a three-dimensional object, you hit a three-dimensional object like a box, like a box made of metal. So definitely the length of that box will increase if you increase temperature. The breadth also will increase. The height also will increase. So in general, that means the volume of that box will increase, and the area will also increase as well. So similar to the change in the length, you remember that I said if the expansion is sufficiently small, delta L over over Li will be equal to alpha delta T. So this is also applicable to volume. So if the expansion is sufficiently small, then delta V over Vi is proportional to delta T. So that I have what I have here, delta V over delta is equal to gamma delta T. Gamma is the coefficient of volume expansion now, because you are dealing with volume here. So that is volume, gamma is coefficient of volume expansion. So I just cross multiply to have delta V is equal to gamma Vi delta T. So, and delta T is change in temperature. That is final temperature minus initial temperature. Delta V is also final volume minus initial volume. So, but I can write it in short form like this equation that I have here. Gamma is the coefficient of volume expansion. Similarly, we can do the same to area, because when you increase temperature, the area also will increase. So I can have delta A is equal to beta A delta T. AI should be AI, that is the initial area. So in this case, this beta is the coefficient of area expansion or superficial expansion. But in most problems, they don't always give us this gamma and beta. What they give us is the linear coefficient of linear expansion. So we have to know this relationship, that gamma, that is coefficient of volume expansion, is equal to 3 times the coefficient of linear expansion, while coefficient of area expansion is equal to 2 times the coefficient of linear expansion. But this assumes that alpha is the same in all directions. What does this mean? It means that it's possible I have a box and the base is made of iron, then the side is made of brass. In that case, this will not hold. So you have to do for each side separately. But this relationship is telling us that, the box or the object is made up of the same materials all around. So take note of that. Then we still look at it and the first law of thermodynamics. Though we did not enter first law, but we enter that during the physical classes. So heat and the first law of thermodynamics. We have heat capacity and we have specific heat capacity. And I told us that its capacity, capital C, that's uppercase C of a particular sample of the substance, is defined as the amount of energy needed to raise the temperature of that sample by 1 degree Celsius. Yeah, when you have a body and you are just looking at, oh, what amount of energy can I supply before the temperature of this body can increase by 1 degree Celsius. So the heat you have added at that point is what is called the heat capacity of that material. But when you have a sample and let me just take this mass out of it and look at the amount of energy I will supply to this the mass I've taken out before the temperature can increase by 1 degree Celsius. That's what's called specific heat capacity. So for heat capacity, we have energy supply per change in temperature. So C is equal to Q over delta T. So that your Q will be C capital C delta T. So that's for heat capacity. So if I define this equation by the mass, that is, if I define capital C by mass, so that's specific heat capacity. You know, C is the heat energy added to a particular sample to raise the temperature by 1 degree Celsius. Let me now say I'm looking at the heat supply by per unit mass. So that will give us specific heat capacity. That's why I say if I divide this thing by M, I will have a specific heat capacity. Okay, I said divide the above equation by the mass M of the substance produces a quantity called specific heat, small c, which is the energy needed to raise the temperature of a unit mass of a sample by 1 degree Celsius. So I divide it, I have this, which I have Q over M delta T. So that when I cross multiply, I will have Q is equal to MC delta T. So this is what you always call MC theta in secondary school. So it's fine. But here I'll be using delta T as I've told us in the previous class. Specific heat capacity, okay, is a measure of how thermally insensitive a substance is to the addition of heat energy. How thermally insensitive a substance is to the addition of energy. That is, if a particular object has a higher C, if they say, the specific capacity of this object is high, it means before you can change the temperature of that object by 1 degree, you need to supply more energy. They say the higher the C, the more energy must be added to a given mass of the material to cause a particular temperature change. Then you have a conservation of energy, that is by it is transferred from one object to another. So I can have that the heat loss by the hot body is equal to heat gained by the cold body. Heat gained by the cold body. Cold body in this case can be many bodies. Can be a body and its environment, and a body and another body. Like you have a cup of hot water, you pour it in another container that's containing cold water, and that container is also a metal or an object that can take it. So in this case, you have to consider the two bodies, that is the cold water and the container, as the cold bodies. So I put minus. Listen, everybody, I've received this question many times, that why is minus in this place? This minus is telling us that the hot body is losing heat. The hot body is losing heat. So this is the formula, MC delta T, that is like MC theta that you are familiar with. MC, but this is telling us that it's for cold body, while this HH is telling us that it's for hot bodies. I put this minus to show that, oh, this hot body is losing heat. You will see the essence of that minus now. So this is MC. Look at this equation. MC delta T. Delta T is TF minus TI. If this for cold body, as I've indicated, you will see that the final temperature is always higher than initial temperature. If I pour hot water in a cold body, so after I've attained an equilibrium, the final temperature will be higher than the initial temperature of cold body. So this is Very correct. Then let's go to the other side. For hot body. For hot body, the final temperature is always lower than the initial temperature. If I now say TF minus T2, that is the final temperature. This should be T. Okay, there, yeah, T2. This T2 is the initial temperature of hot body, which is the highest temperature of them all. So this will give me minus, so that this minus will cancel this minus, and I have normal thing that I have there. Another way to do this is to bring the initial temperature of hot body to the front and bring TF to the back, so that this you now cancel this in that case. You not put this minus. You not put this minus in that case. But in real sense, this what happen is always final temperature, final something minus initial something. So if you say final temperature here, which is lower than the initial temperature, it will give you minus. So which will cancel this minus at the end of my calculation. So we did latent heat. So I told us that there are situations in which the transfer of energy to a substance does not result into a change in temperature. That is, when you are supplying temperature to a particular object and you see that you are supplying it rather, and you see that temperature is not changing. So that's what's called latent heat. It means at that point, the object is trying to change from the form it was to another form. Maybe you are eating solid now. You are eating solid, the temperature begin to increase. Then you get the point that you are eating it and you notice that temperature is not increasing again. It means at that point, that solid want to change to liquid. So if the energy supply to it, instead of using it to increase its temperature, is just using it to change from one form to another form. And that's what's called phase change. This is always the case when phase change occurs. And I said the common phase changes we have is change between solid and liquid, and change between liquid and gas. So that's the common one. That is something change from solid to liquid, or some change from liquid to solid, or some change from liquid to gas, or from gas to. These are the common changes we know. So when solid changes to liquid, that's what's called melting. So we have said this before, and I believe many of us that went to a good secondary school know this before. Liquid to solid, when liquid changes to solid, it's called freezing. Then liquid to gas, it's called vaporization. When gas changes to liquid, it's called condensation. That is, the gas has condensed before you can see. That's what happens when you are boiling water and you open the cover. You will see some droplet of water on your cover. It means as the water is changing from liquid water to vapor, so they are condensing on the cover. There are still other changes that we know, but they are not that common. So we have at times when you are eating solid, instead of that solid to change to liquid before it change to gas, the solid will just change directly to gas. So that's the case of iodine. When you pick a solid iodine and you are eating it, instead of you to see liquid first before you see gas, the thing will just change directly to gas. So we have camphor, we have ammonium chloride. This process is what is called sublimation. Then the reverse process is what's called deposition. That is when gas changes to solid directly instead of passing through liquid state. So it's what's called deposition or the sublimation. So I think the last thing that we will look into this morning before we begin our interaction is microscopic description of an ideal gas. Macroscopic description of an ideal gas. So what is an ideal gas? An ideal gas is a gas that is kept at a very low pressure. That is a low density gas. So that's an ideal gas. For an ideal gas, PV over NT is always a constant at a particular pressure, volume, and temperature. This value for a particular gas, so this value is always, that is when you have a gas, maybe the pressure increases and the volume decreases. When you check the volume you have at that point, multiplied by the pressure, over the number of mole and that at that temperature, you get a value. When you either reduce the volume again and reduce the temperature or increase the pressure, when you still get the same gas, the same system, when you still pick the pressure at that point and the volume, you multiply them and you divide by the number of mole times the temperature at that point, you still get the same value you got in the first place. The equation that relates the state variables. I told us what are the state variables. We have volume, we have temperature, and we have pressure. That is, these are the variables that define the state of a system. Okay, that define the state of a system. So we call them state variables. State variables. The equation that relates these state variables is called the equation of state. Equation of state. Equation of state. And this equation is a very complicated one, but it's very simple for ID gas. For ID gas, that's why you can be doing that in 100 level. For higher level, the equation is a bit complex. So it's very complicated, but simple for gas maintained at a very low pressure. And you know, gas maintained at a very low pressure will behave like an ID gas. So suppose an ID gas is confined in a cylindrical container whose volume can be varied by means of a piston that is shown on the right-hand side here. So this is a container in which there is a gas and there's a piston, a movable one that can go down. If the piston goes down, the volume will reduce and the pressure will increase. If it goes up, the volume will increase and the pressure will reduce. Okay, we can calculate the change in the volume by using this simple formula, the area. So this area can be the area of the piston times the distance between the initial position of the piston and the final position of the piston. So this just the volume change. So I say experiments have shown that for such a system, for this kind of system that I just showed you now, so we have a piston, we have a gas in a container, blah, blah. So when the gas is kept at a constant temperature, its pressure is inversely proportional to the volume. What we are saying is that, let's say this is a system and I've kept the temperature constant. That is, I do not allow the temperature to change. Anytime I increase the volume, that is, anytime I move the piston up, it means you know there will be more space in the container. It means the volume has increased. Then there will be reduction in the pressure. They have the pressure and the pressure and volume have an inverse relation at a constant temperature, and that's what is called a Boyle's law. Boyle's law in secondary school. Boyle's law. We also call Boyle's law in. Because that's the explanation that when I keep the temperature of a system constant and I increase the pressure, the volume will reduce. Or when I increase when I reduce the pressure, the volume will increase. They have inverse relation. So P is proportional to 1 over B. So that's Boyle's law. When the pressure of a gas is kept constant, let's say we keep the pressure constant, the volume and temperature has a direct relation. That is, when one of them increases, the other also increases. When I increase the temperature of a body and I keep the pressure constant, when I increase the temperature, the volume also will increase. When I reduce the temperature, the volume also will reduce, provided the pressure is constant. That's what's called Charles' law. Charles' law. If you combine the two laws now, so we have what is called the equation of state. We have what is called the equation. These two observations are summarized by the equation of state for an ideal gas. So, and where R is the gas constant, and P is the pressure, V is the volume, T is the temperature, N is the number of mole. And N can be, you can use this simple relation to find our small n, capital N over NA. NA is what's called Avogadro's constant, while this capital N is the number of molecules in that gas. So if I remove this N in equation star, I will just put capital N times R times T over NA there. over NA. But R over NA is still another constant, which is called KB, Boltzmann constant. So if I remove that, this equation star will turn to equation star star. So this is another equation of state. Another equation of state. And they are known as ID gas law. ID gas law. So I think we can stop here so that I can take some questions and comments. Okay. Okay, yeah. People already raising their hands. So you can unmute yourself and speak now. But please, don't make the class to be too rowdy, please.
Good morning, sir.
Good morning. Welcome.
Yes, my question is that what is the relationship between pressure and temperature?
Relationship between pressure and temperature.
Yes, sir.
Let me give you as an assignment now. Yeah. So you can use no, it's that I want to submit.
Please, I want to answer the question.
I just want to fight the game.
Please,
Okay, you want to answer the question? Okay. I'm listening now.
Sir, good morning, sir.
Good morning.
Sir, yes, sir, I would say the relationship between temperature.
So you will, okay. If you use use this equation, you will look at their relationship. You will see the relationship. What's the relationship between pressure and volume?
Pressure is mass over volume.
Pressure is what?
Pressure is inversely proportional.
Pressure is
force over area, not mass over volume.
Hello, I cannot hear you.
Pressure is force over area.
Force over area. Leave area now. Leave area now. I mean, in this sense, what's the relationship between pressure and volume? I mean, in this sense,
proportional volume.
yes.
The relationship between pressure and temperature. Pressure is inversely proportional to volume.
Yes.
Allow one person to talk.
Exactly. Then in this case now, what's now the relationship between pressure and temperature now?
Directly proportional
to temperature.
Yes.
Directly proportional to temperature.
Now. Yes, now that's why you have P1 over T1 times V.
Indirectly proportional, sir.
Yes. So you look at this, because if I have an inverse and I want to find the constant, I will have a PV is equal to a constant. That is when I remove this what's it called, this proportionality symbol, I will have a P is equal to K over V, so that my constant will be what? My constant will be P equal to PV. So, but in this case, let's use the general what's it called? General equation now. So we have PV over T is equal to NR. NR is a constant. That is equal to, it's equal to R. PV over NT is equal to, who is that? PV over NT is equal to R. R is a constant in this case. You see that you have P over V, P times V over T. So P and V, we have direct relation, where P and V have inverse relations. So there's a direct relation between them. So there are many questions that when you play around the equation relating them, you'll be able to get your distance out. So there's a relationship, there's a direct relationship between them. So any other thing?
Sir,
Is it my network or their network?
please,
I cannot
that
really tell.
that worked example that you did last lecture.
Okay.
Please, I did not understand it.
The last one.
The last third this thing. The worked example.
The last third. I don't understand that English. What's the last third or?
I
You
said
mean
the
here?
last that we did last lecture. The third one.
Oh, let me.
The third worked example.
Let me share my screen. Let me share my screen.
Good morning, sir.
Yeah, good morning. Let me answer that guy for. Is it this question? Is it this?
No, not this one. Not this one.
Is it this?
Yeah. This one.
This one? Okay.
Yeah. This one, yes. This one.
Okay. Okay.
No, sir, that one that has to do with rates.
With rates, okay.
Yes. Yeah, this one.
That's this one.
Yes, sir.
Okay. Let's say water flows. Okay. Water flows. What's wrong with this thing? Let me minimize it. Okay. Water flow at the rate of this. That is at the rate of 0.15 kg per minute. That is every minute. Every minute. Okay, let me mute people so that we listen. Okay, I've muted them. Water flows at the rate of 0.150 kg per minute through a tube and is heated by the heater dissipating at this value. The inflow and outflow temperature are this and this, 15.2 and 70.4 degrees Celsius. When the rate of flow is increased to this value, that is 0.2318 kilogram in every 1 minute. The rate of heating increased to this, then the inflow of water remain constant, remain unchanged. Find the specific heat capacity water and the rate of loss of heat from the tube. Yeah, they said the tube and that tube the rate of flow of water. Rate means what is the amount of water I'm getting at a particular time. At every 1 minute, this rate at which the water is you have 0.15 kilogram at every 1 minute through that tube. And there's a heater eating it at this rate. When the water enters at this temperature. Before the water will leave the temperature has become this because there's a heater eating it at this rate. So, but when the rate increase to this, that is when the rate of water increase to this, that is at every 1 minute we get 0.23118 kg is flowing. So the heating rate becomes this. But the temperature of water, the inflow temperature is the same as the inflow temperature in the first place. The outflow temperature is the same as the outflow temperature in the first place. And that's how we calculate the specific capacity of water. So in this case, this next time again. Okay. In this case, I will use don't forget that it is heater that is heating the water. So that's the rate of heating, which is power now. Look at this unit here. This is power. This is like energy over time. And you know formula for power is energy or work done over time. So if in the first case, I'll treat it one by one. In the first case, this power is equal to MC theta, that is MC delta T, then plus the little amount. This heat that this heater is giving to the water is absorbing it. and some amount is being lost to the environment. That's why they say calculate the rate of heat loss from the tube. Yeah. So I will just have a 25.2 is equal to MC delta T plus a little amount that is lost to the environment. That's why I use this little formula here. P is equal to MC delta T plus HL. HL is the little amount that's being lost to the surroundings. Why this MC delta T is the amount that water is absorbing from the heat from the heater. But you see that this MC star is in energy, right? But this is power. This will be the same if I divide this thing by T. Are you listening? If I divide, that means it will be MC delta T over T, that is over time, then plus heat from rate of heat loss. That's why they give you mass. So I don't need to divide it by another T because the mass is already giving me per minute. That is divided by time, mass divided by time. That's why this can still be called power dissipated or power absorbed, the rate of power absorbed by the water. Because this M is not just under mass, it's mass per minute. So this is the formula I will use. The power dissipated by the heater is equal to the power absorbed by the water and the one lost to the surroundings. I will now use the first case. In the first case, this is the rate at which the heater is dissipating the power. This is the mass giving us per unit time per minute. So I divide by 60 because 1 minute is equal to 60 seconds. So I divide by 60. Then this is the C you want to calculate. This is temperature change. The outflow temperature minus the inflow temperature. That is the final temperature minus initial temperature. So plus HL. HL is the one that is lost to the surroundings, as I've said before. So that's the first case. In the second case, the heating rate become this, that's 7.8, which is equal to the mass we are getting per seconds. Because it's per minute, I divide by 6 to get mass per second. So that will be normal power that we know. Times the C, because it's still the same water. This C and this C are the same. So times temperature change. They have the same temperature. That's why they say the inflow and outflow temperature remain the same. So they didn't change. So that's why the change in temperature in the two cases will have the same value. So plus HL, the one lost to the surroundings. So I just press my calculator to have this value, which I have here is 0.025 C times change in temperature plus HL is equal to 25.2. I brought this one to the other side so that it will look exactly like a simultaneous equation for me to solve. I can leave this on the left hand side, but I want it to look like a simultaneous equation to solve because I have two variables to get now, and I have two equations. That means I can solve the two equations simultaneously. For the second case, I have this. If I divide 0.2318 by 60, I will have 0.0039 times C, times temperature change plus HL. So I have this. I still write my 7.8 on the right hand side so that it look like a normal equation. So if I multiply 0.025 times 2.2, I will get 0.005 C, this C. Then plus HL is equal to 25.5. Then the second one, I have this. So I can now solve this equation simultaneously. So I can just use the elimination method because HL here is the same as HL. I can just subtract this equation from this equation or this one from this one to solve what I solve. I still solve equation 3 and 4 simultaneously. So when I subtract equation 3 from equation 4, I have this. So that my C will be 12.6 divided by 0.0030. So to have this. So once you get your C, you just use one of the equations here, either this or this, to get your HL. You've gotten your C, put your C here, bring it to the right hand side so that your HL will be 25.2 minus whatever you get when you multiply C by 0.055. So that's what I have done. Let me unmute you so that you can tell me if you are for. Okay, you can unmute yourself.
Yes, I understand that.
Okay. Power is energy over time. This one is over time. That's why they give you per minute. That's divided by time. So it's the power. 3 hours. Okay. Any other thing?
Sir, please, can you put it in the slide with the question?
Can I?
Put it in the slide with the question.
Okay.
Thank you, sir.
This one?
Yes, sir. Thank you, sir.
Sir, the last example you gave.
Okay.
About what mass of steam initially at 130 degrees Celsius. So I don't
Okay.
understand the second stage there.
Okay. I want to leave this page now. I want to go to that question she's asking. Where is that? You see in this lecture or the previous one?
Yes,
this one.
Underline. Yes, this one, yes.
Only what mass of steam in the second what?
Sir, just explain the question to us.
Okay, I should explain the question.
Yes, and the solution.
Okay, what mass of steam initially at 130 degrees Celsius is needed to warm 200 grams of water in a 100 glass container from 20 to 50? They are asking you that we have a container and the mass of that container, like a glass container, is 100 grams, and that container is having water inside it. The mass of water inside it is 200 grams, and the container and the water, they are at this temperature, that is, they are 20 degrees Celsius. Now say they now pick steam with temperature 130 degrees Celsius. They pour it. They begin to mix on the temperature. The final temperature becomes 50. That's what mass of that steam is needed to change the temperature of the water and the container from 20 to 50. Yeah. So you have to consider different stages in this case. Let's pick the hot object, which is the steam now. You see that 130 is higher than the temperature the steam will change to water. Steam means gas. Mass of steam, that's gaseous water. So when you put 130 degrees Celsius in water of 20 degrees Celsius, the temperature of this steam will begin to reduce. Once it gets to 100, because the final temperature is 50, that means the temperature of the steam drops from 130 to 50. So the steam has passed through different stages. Number one, from 130 to 100, the temperature decreases. So you calculate the energy lost by the steam. At that point, I'll use MC delta T. Delta T now, change the temperature is 30. That is 130 minus 100. That's 30. Are you listening? Then when the temperature gets to 100, don't forget that water will always change from getting to 100. So the steam will change to liquid water at 100. That's where latent heat comes in. So use mass times specific latent heat of vaporization of water at that time. That is, water will change from vapor to liquid at that point. Then after it has changed to liquid, then the temperature begins to drop from 100 until this 50. That's why the steam undergoes 3 stages. That's why I put in the solution that let's consider. Okay, I say in this case, the gaseous water, that is the steam, which is the hot body now, undergoes 3 processes. Number one, a decrease in temperature from 130 degrees Celsius to 100 degrees Celsius. So I will calculate the energy, the steam lost in this case, because its temperature dropped from 130 to 100. So I will use this formula, that is MC delta T. Delta T means change in temperature. So which is this. Then after getting to the 100, the steam want to change to liquid. That's condensation at 100. Don't forget that the steam point of water is 100. So that is water will change. If it's in liquid, it will change to vapor at 100. If it's vapor or if it's a gas, it will change to liquid at that 100 again. So that's why, because we are using steam, it will change to water at 100. And this second stage, that's latent heat that you apply, latent heat of vaporization. That's why I use this one. Energy involved in the second stage is ml. ml is a mass times latent heat of latent heat of vaporization of steam in this case. So you have this in second stage. Then in the third stage,
so my question is in the second stage.
Okay.
So how do you get minus for that second stage?
Look at this look at the bracket now. Okay, in this second stage. Okay, that's what you are asking. But I told you that hot object always loses it to cold object. From this, okay, let me. If you remember where I started from, I said Q code. This look at this equation. Q code is equal to minus 2 hot. This minus is telling us that the hot body is losing it. I've said that many times. So listen, because I received questions on that. That's the first thing I said when I get there. That Q code is always equal to minus Q hot. This minus is nothing but just telling us that this hot body is losing it. That's why we put minus in the front. And if you look at it, so I've calculated the energy lost by that body, but to show that it's energy lost by the hot body, I put this minus. So if you don't want to put, listen, if you don't want to put this minus, you must have done something here so that you have positive. You know, this is final temperature here. You must have brought 130. I've explained this in the first lecture. It's getting to, so you can bring 130, that is initial final temperature, initial temperature minus final is 100 now. So you have plus here. You have plus here so that you can see have plus here, but you have to bear in mind that this is hot body losing it. So in this case too, 100 will come before 50. You have, so that you have plus 2, so that you can add all of them together. Do you understand? You can do it in that case also. So after everything, you now say Q hot is equal to what's it called? Q hot is equal to Q code. In that case, the method you want to use. So it's different to get the same result. So what is okay?
We have another class now. Why don't you apply the subtraction in the first stage? You did not put the minus sign in the first stage. Yes, you did not put minus there.
This will tell you, this will, okay, automatically this is the minus. If I want to put minus, I will interchange this. I'll put my minus here. What is 130 minus? What is 130 minus 100?
That's 30.
That's 30. If I interchange this, I will. That's when I'll. But this one is already inputting that minus. That's why I did not bother to put it here.
Okay, sir. Thank you.
Thank you, sir. We have another class now.
Okay. So we are having our tests. Okay, maybe we decide I want us to have it tomorrow or when?
Tomorrow, sir. Tomorrow.
Tomorrow is fine, sir.
Monday.
Tomorrow is okay. Tomorrow.
Please, on Monday, sir.
Monday,
Please, on Monday.
Monday.
We are having CHM test on Monday.
Right now.
Okay, we talk on Telegram.
Monday. Will you all come and shut up?
There is Odu on Monday.
Hello, sir. To know about that, use that Telegram page.
Sir, please, Monday.
We have tests on Monday already.
Sir, please Monday. Sir, please Monday.
It's festival.
We
No,
there's
no,
public holiday on Monday. Okay, that means we do it on Tuesday.